This is a demonstration of what CanberraUAV is doing for the Outback Challenge in 2018. And we're just packing at the moment and we're heading up to Dalby for the challenge on Friday. And I thought I'd take an opportunity to show in simulation how we're planning to tackle the challenge this year. So what I've got here is a simulation of a quad plane, simulating our octa-quad Porter, and also a simulation on another screen here of a flying wing, and that flying wing is acting as a relay aircraft, a radio relay aircraft between the Porter and the ground station. So what I'm going to do is I'm just going to tell it to start the takeoff, and then I'll explain while it's on its way to the destination what it's doing and how it's doing it. So what we've got here, one of the challenges in this year is that it all has to be hands-off. Now, I'm not going to do this demonstration completely hands-off because I am going to be demonstrating, going around with the mouse and showing what's happening with the simulation, so you can sort of see what's going on. But we have done multiple missions completely hands-off, and it is able to be completed without us touching keyboard or mouse the entire mission. Now, you'll notice that we have two planes on the display here. So we have our Kraken, which is waiting on the runway here. And that's waiting for the release the Kraken command from the Porter when the Porter gets to a later waypoint towards the end of the mission. You'll also notice something else unusual. There's a lot of wildlife in the area. So you can see there's some eagles, there's some migrating birds, there's some clouds, there's also some other planes up here. And that's because in the challenge this year, one of the challenges for the optional extensions to the challenge is to avoid a whole lot of synthetic obstacles, dynamic no-fly zones as they're called. And so we've simulated those, and we're randomly generating obstacles here. So we've got randomly generated planes, and the yellow clouds represent weather systems. The white hawks here represent the birds of prey, and you've got to make sure you stay above those because they can dive bomb, and if you go under one of them, you don't successfully complete the autonomy extension to the challenge. You've also got to stay inside this geofence and stay clear of these red exclusion zones. So I've scattered a few exclusion zones around the area. So this is inside ArduPilot. We've extended ArduPilot's avoidance code to automatically avoid all these obstacles. So we don't have to do anything at all. We just tell it to go to its destination, and it will strive to complete its mission while avoiding all of these obstacles. And so just to demonstrate that, you can see it's coming up to a waypoint up here. And after it turns around that waypoint, it would normally come back this white track here. And I'm going to do a little bit of weather manipulation and drop a cloud in there. And so by dropping a cloud on its track, it's not allowed to go through that weather system because there's a exclusion zone represented by that blue circle around the weather system, and we have to stay outside of that. So the plane has automatically started tracking around it. It's also tracking around this exclusion zone here. You'll notice, however, it's quite happily going near this migrating bird, and that's because that migrating bird is at 301 meters above the ground, whereas our aircraft is 120 meters above the ground, which means we have enough vertical separation by the rules to not worry about that migrating bird. And so now it's gone around this exclusion zone here, and it's avoided that cloud there, and it'll now go around there and come back and track back to this waypoint to continue the mission. So I'll also show you now what's happening with the Kraken. So the Kraken is our second aircraft, and it's sitting waiting to be released, and you can see there's a countdown here. It'll release itself after about 15 minutes if it doesn't get a command from the Porter. But when the Porter gets to a particular waypoint, it'll actually send a command across to the Kraken to say, please take off. And that's because the Kraken is being used as a radio relay, but it's only really needed when the Porter is at the far end of the area and is then doing the search and the landing at the far end, beyond visual line of sight landing. And then having the radio relay in the air is very useful. So the porter will automatically tell it to release takeoff and then fly this pattern. So it flies this pattern near the home, just acting as a very high antenna mast uh, for the porter. All right. So what we have there is the Kraken sitting waiting for the porter. The porter has now avoided these little obstacles and is going back to its main track up here. Notice we've got 4 maps on the display here. These multiple maps are to allow us to complete the mission without touching the keyboard or mouse while maintaining the awareness of what's going on with the aircraft. So we have this map which tracks along the aircraft, set to a couple of kilometres wide. This map here normally would cover the whole range, including the geofence, but I'm actually zooming in and out just to demonstrate things for this video. And the size of these maps, I've got a limited laptop display here at the moment. We'll normally be using big screens and have much larger maps. Then we have the search zone map here. The blue circle represents the area that we are allowed to search. And I'm just realizing that I've done a previous test here and the waypoints were set up already near the true location of our synthetic object. So what I've done is I've just reset the target location back to one that isn't anywhere near where it's going to find the object. The target, there's a red and blue target we've got that the farmer that's in trouble has put out for us, and our aircraft will automatically find that target and geolocate it and then choose a landing location and land. We then have a zoomed in map here which will automatically be zoomed in down to just a few meters around the landing zone, so we can see a really close in view of what the images look like of the target near the landing zone. All right, a few more features I'll show you before we get on with the rest of the mission. Actually, we'll see here it's just about to reach the point where it will tell the Kraken to head off. So when it reaches this waypoint here and it starts on this leg, then it's going to inform the Kraken that it's time to take off, and the Kraken should at least, assuming that everything works correctly, should launch itself into the air. So just waiting for it to reach that, and it's only 0.1 of a nautical mile to go for that waypoint. There it is, and in a few seconds now it'll be checking that the Kraken should be released, and we'll be sending that command. There it is, it's sending a releasing Kraken. So we are now releasing the Kraken, and the Kraken over here has now automatically started its takeoff, and it's going to start circling around here. Now it of course does all the same avoidance of weather systems, and in fact it has features. For example, you'll notice it had something called a nav delay airspace clear. So before it takes off, it automatically checks that the airspace is clear to a certain radius and height and time, and it won't allow it to take off until the airspace is clear. The same thing for its landing sequence. It's got conditional jumps based on the airspace clear. So when it comes back to land, it does landing aborts based on whether the airspace is clear, and all that sort of thing. So the same with the porter. It has the same system where it automatically delays takeoffs based on airspace clear and delays landings and does landing aborts based on obstacles, because these dynamic no-fly zones can appear at any time. They won't appear within 500 meters of our aircraft, but they can be going quite fast, and so we have to be ready to avoid at any time, including on a landing approach. And so it will automatically abort a landing approach if it needs to. All right, so the porter is now well on its way. It's got a distance of 1.6 nautical miles before it reaches the search area. So good opportunity. I'll come and have a show you what the search area is like. So I'll just zoom in here, and we can see the blue circle is the area that the farmer has told us that he's got an approximate GPS coordinate for where he's standing, ready to give the blood sample to our aircraft. And So it's a radius of 100 meters about that the target could be in that we have to search with the onboard imaging system. We're generating random images, so you can see here this preview window every 4 seconds is showing an image from the onboard camera system. Because this is a simulation, these images are just taken from other flights that we've done at our local airfield, but they do get overlaid automatically the images in the target images that we're searching for in the right location. So these synthetic images will have the correct georeferencing of the target within them so that the onboard imaging system can run in the simulation. All right, so you'll notice that it's a sort of a cloverleaf type pattern, the search. That's to reduce the systematic errors you get from small amounts of roll and pitch error in the aircraft and timing delays from GPS and timing delays from the camera. By approaching the target from all directions and averaging the positions, we can get a very accurate georeference. And we typically get sort of 1.5 meters or so in our georeferencing for the landing position. So it's flying this sort of cloverleaf pattern. And while it's flying the cloverleaf pattern, it's looking for images. And then it will automatically shift this search pattern based on what it finds. So when it locks on to the target, and it gets confident about the target, it will shift the entire cloverleaf to be above the new target location, and it will do that at least 3 times. So we can now see it's coming into the search area. I'm just going to check that I've got the speed up. Yes, the simulation speed up is set to 1, so normal real time. All right, so it's now flying in the search area. It's just gone into the blue circle, and it's now going to start flying this pattern while it is looking for the target, and it doesn't know where the target is within the circle, so it just flies the entire region and hopes that it flies above the target. Because this cloverleaf pattern covers the entire area, it will in fact, it's sure to find the target at some point, although of course its view could be obscured by trees or other things on the ground. So in reality, it might be that you only find the target from particular angles, depending on what sort of obstacles there are on the ground that might be obscuring the view, particularly trees. All right, so it's coming around here for another pass and flying at about 45 knots, so target of about 25 meters a second. The Kraken's flying a little bit slower, about 13 meters per second. There it is crossing the search area again, and it should, assuming I have set up the synthetic images correctly, it should be finding the targets fairly soon. Let's see whether it finds it on this next pass. It will keep searching there until it finds the target or it runs out of fuel. But of course we can intervene. We wouldn't then be doing a fully autonomous mission, so we wouldn't be eligible for the grand prize with full autonomy if we have to intervene. But we can of course intervene and assist it with its operation if things aren't working correctly. And I suspect I have mucked up the target coordinate here, because it should have found the search area by now. I'm just going to have a look at our synthetic object generation. Oh yes, we are in fact getting objects there. So it is occasionally generating objects. I'll give it a little bit longer to have a chance. Sometimes when my machine is very overloaded, I get delays and problems with the georeferencing in the simulation. And if you have a look up here on the right hand side, you'll see that all 4 of my CPUs are completely maxed out running the simulation, partly because I'm doing the video recording at the same time. And so that can cause it to get a large backlog of images and having trouble with the georeferencing. It actually works far more accurately on the real aircraft than it does in simulation, just because it's not trying to simulate the physics of all the aircraft plus all of the other subsystems at the same time. All right, let it go around another couple of times and see whether it finds it. Meanwhile, we can go over and have a look at what the Kraken has been doing. And we can see there that the Kraken is flying around. It's been doing some avoidance. and you can see that it's heading around to these waypoints, but it's been there was an aircraft that went past that it had to avoid, so it's basically trying to avoid all these obstacles while flying this very, very simple path here. Back to the port again. We have a look, and now it's actually got an image, so it's found the first example of the target. There it is there, and it's just flying over that location again. And there it's got another sample of the target and another one there. And you can see now that it's got these 4 examples of the target, and it's now moving the search. So what it's doing is it's automatically shifting the search pattern to be over those targets that it's found. There it goes. That's moved it a bit closer. Now, it didn't move it all the way. It deliberately only moves the search area a certain distance each time, just in case it's got a false positive on the target, have more chance that it can find the real target. And so the next time it shifts it, which will be in less than 2 minutes time, it will shift it probably to the final location. And you can see it's getting the targets quite regularly now and really not having any trouble finding it. And we can have a look. There's a number of things about the target here. We can see, for example, down here we have these landing zone estimates. So the inner green circle is where it would land based on the current estimate. It automatically eliminates outliers, and it also sorts the images based on the roll and pitch of the aircraft and the quality of the images and various other criteria. And it's then working out which ones it will use as the basis for the landing zone. Then the outer green circle is its error, the estimated error in the landing position. It's in fact encompasses all of the images that it's decided to use as part of its estimate, and the inner circle there is a 2-meter circle which just circles the landing position that it's going to be using. All right, so it will shortly be shifting that landing position again, and once it's done that at least 3 times, if it's got a sufficient number of targets that have shown up, then it will initiate an automatic landing. And this is the point when we first got the target where we would show the organisers the location that it's decided to land and get the okay from the organisers. Because it's fully autonomous, we would have to intervene and tell the aircraft not to land. Otherwise it will automatically land on the target unless we intervened. And so the organisers will tell us that no, we're in the wrong location and we can't land there if the target is bad. All right, now it's shifted the search again. You can see that the search is now directly on top of these targets. And so it's now quite happy about the landing location. It's now doing extra passes over it to refine the precise coordinates of the target. And these ones are very important. To fly over it when the wings are level directly above the target gives the most accurate georeferencing. And it's able to then automatically sort the targets that it's found based on how level it was and how centered it was in the image, etc. And from that, it can work out, whether it's got a good view. So I'll just zoom in there to sort of show you what's happening with these images. And you can see there's a whole group of images in one location here that it's placing the target. So it's choosing for the target location, and it'll move those waypoints at least one more time before it finally decides to initiate a landing. Now the landing, it does a pre-landing. Up here it's got a pre-landing circuit, and that pre-landing circuit is so that it can check for airspace clear, but also give time for us to intervene and tell it not to land. So we'll go into this pre-landing circuit, and then if the airspace is clear, in the pre-landing circuit, it'll start the actual landing approach for a vertical landing on the target. And so any minute now, it'll decide that it wants to land. So meanwhile, the little Kraken has been avoiding these obstacles up here, and it's not worried about that eagle because that eagle is well below the height it's flying at. It's at 181 meters and the eagle is only at 90 meters, so that's well above the clearance radius, so it's quite happily doing that. It's a lot of wind though. We've set up simulated wind for the Kraken here, so the poor little Kraken is fighting a significant wind, but it's making progress anyway. All right, so here we are. In fact, the porter now has decided to start its landing. So it's shifted the landing location to its final landing location, and it's now coming up towards the landing. And what I'm going to do is I'm going to really mess with it by dropping a cloud right in the middle there. And so now it's panicking because I dropped the cloud right next to it. It's trying to run away from that cloud as fast as possible because in fact it was a breach of the perimeter of that cloud, the allowed exclusion zone. So now what it's doing is trying to get to its waypoints while avoiding this weather system, and it'll keep doing that until it can actually get to those waypoints. But it's also now automatically gone back to the landing approach, and it will wait for this cloud to pass. So if we just wait for that to drift on across there, once it's drifted over, then it will be able to try another landing. I should have chosen a faster moving obstacle than a cloud, like a bird or something. Clouds are, the weather systems are very slow moving, maximum of about 3 meters per second. And so it can take quite a long time for it to shift off. In fact, I think I'm going to do a little bit of weather manipulation and go and remove that cloud. So goodbye cloud. And when that disappears in a few seconds, when it times out, then the aircraft will be able to go back into its landing approach pattern. So there it is, it's back in its landing approach pattern, and it will now see whether the airspace is now clear, and it should find it is indeed clear. In fact, we can see that we've got fully green on the dynamic no-fly zone status up here, and so it's now going for the full landing. At each of these points, it again checks for airspace clear and decides whether to abort the landing automatically, but doesn't look like there's going to be any obstacles. Looks like it's going to go straight in. So there it is, and you can now see it appearing on this map, coming in for a vertical landing. And it's slowing down, it's engaged the vertical motors, and you can see the current, the simulated current on the motors has gone up to 60 amps, which is about the current we use for landing. You can also see it's getting lots of the target. And there's the target on this little image down here appearing in the middle. It'll get bigger as we get lower, and we can see some quite large versions of the target as we come down closer to it with these sort of simulated images. It's down to a height of 21 meters, so 90 feet. AGL, see it's about 38 feet. The rangefinder is showing about 5 meters here, and we're nearly down to ground level. About 3 or 4 meters, it's gone into its land final, which is where it slows down its vertical descent for the landing. And it should then land there down to 0 meters. It'll disarm in just a couple of seconds. It's disarmed, so it's now landed. All right, so we are now landed at the far end. Oh, the thing I thought I'd mention is you'll notice some delay on these links. We're running 3 radio links up to the aircraft. One is the relaying with the RFD900X, and then 2 UDP relays via 3G modems. And we're running on all the real radios. For this simulation, we've set up the simulation to talk via exactly the same radios that we are using in the competition. That allows us to simulate all the sort of packet loss and types of network delays that we get in the real competition. Right, so now what I'm going to do is I need to press the button, the little button where Joe goes out and presses the button when he puts his blood sample on board, and I can simulate pressing the button like this. And so it's now got a button press, and we can see a countdown of the button here down to sort of 50 seconds, and so it's going to count down for 1 minute until it has timed out. It's a 1 minute wait, and once it's done the 1 minute wait, then it'll automatically take off. If we have a look at the mission here with the takeoff, there's some interesting things. It's got this nav delay button, which is a new Mavlink mission item we've added, and then it's a delay of 60 seconds, followed by priming the engine, the petrol engine for takeoff, and then doing an arm of the motors, and then forcing the fence to be on for takeoff. It actually is already on, but it's going to force it on anyway, and then it's going to do a VTOL takeoff and start on its way back. So it's got another 7 seconds or so before it does the takeoff, and it would abort the takeoff if there was any obstacles. So if there was any birds or planes or whatever in the area, it would automatically abort the takeoff. Once it's started the VTOL takeoff, however, while it's on the vertical motors, it will continue the takeoff and then transition. So it has a nice large exclusion zone that it uses before it allows the takeoff to make sure that the airspace is very clear. So it's now the RPM on the petrol motor is coming up and it's starting to climb, and it's now heading back towards home. And so it's left that search area there, and you can see all of these targets that it found very nicely, and it landed nicely on the correct location. So now it's heading home. And once it gets back to this waypoint here, it'll tell the Kraken that it's no longer needed, and it'll automatically tell the Kraken that it can then come in for a landing. So we just got to now wait for it to do that. And it's rather tedious waiting for it, and it's getting late here, so I'm just going to speed up time a little bit so that the simulation runs a little bit faster. And so that just means we won't be waiting quite so long for it to make its long journey back to base. So we'll go and have a look and see what the Kraken's been up to, and we can see that it's just on its lonely time sitting here waiting for the porter to tell it that it can land. And we can see all these obstacles around it. Just right at the moment, there aren't any dynamic no-fly zones that it has to worry about. So it's quite happily coping. All right. And I've actually got the wrong EKF running, which is why the wind estimate was wrong. There it is. The wind estimate, I've actually got 9 meters a second, 18 knots of wind. So rather a lot of wind, given that it's only flying at 27 knots. So that's why it's crabbing so much in this. And that makes things interesting for the avoidance, which is why I had the wind up so high, because the avoidance algorithms have to take account of the wind speed and direction in order to be able to correctly plan the avoidance of all of these obstacles. And so testing with a significant wind is quite important. All right, so the porter, I'll drop the porter back to normal simulation speed, and you'll see it'll come up to this point here and then head up towards this waypoint. When it gets there, it'll send a recall message to the Kraken, basically saying that the Kraken is able to land because it's now within a good range of home and it doesn't need the radio relay anymore. So just another couple of seconds and it will be doing that. There it goes, going there, heading back towards this waypoint. Just a few seconds now, we should see a recalling Kraken message. Any second now. Nope, hasn't sent a recall Kraken. Have I got it set up correctly for this one? What waypoint is it heading towards? 59, waypoint 59. And yes, there should have been a recall Kraken being sent out there as it's heading towards waypoint 59. So that is something that I will have to have a look into and see why it's not recalling the Kraken. The Kraken will automatically land based on its flight time, but it'll be rather tedious if the Kraken is up there for 30 minutes while the porter is... it has sent the recalling Kraken. It just delayed it a bit. All right, there you go. So it now has in fact told the Kraken to go home. It just took a bit longer. So the Kraken is now coming in here for its landing approach, and the port is coming in the similar time. So normally these waypoints are much further apart, and the recall Kraken message would be sent when the porter is about 7 or 8 kilometers away from home. So the Kraken would have plenty of time to land. In this particular case, I've got a smaller mission. I've deliberately made it smaller just so this video isn't quite so long. And in this case, the porter and the Kraken are actually quite close to each other. But I still think the Kraken is likely to be able to get home and land before modulo the wind, of course. The Kraken, yes, with the wind up this high, its ground speed is very, very slow. It's only managing a 12-knot ground speed. And it's also a crosswind landing that it's set up for. All right. Okay. So the porter, meanwhile, is heading off on its path up here. So it's going to head off up there, and then it'll come back and land vertically at home. And it's got to avoid, of course, this static no-fly zone, these exclusion zones along the way. This one is a fair way, I think. So that one is a distance of 93 meters. So it will have to turn just a little bit. So it'll probably bow out its path because I've got various avoidance margins set. In ArduPilot, you've got these margins for avoiding different types of obstacles. So exclusion zones we've got as 200 meters. So it'll have to actually go quite a way out of its way here to get around that exclusion zone. So I expect it'll start turning there fairly soon. There it goes. And it'll curve around that path to make sure that it stays more than 200 meters from the exclusion zone. It'll actually go 280 meters because I've got a thing called avoidance margin wide, which is the extra avoidance distance it uses if it's not in contended airspace and it's got the available space to use it. The 200 meters is the absolute minimum, and then it'll try and go an extra 80 meters. It's also got margins for height and margins for the fence and margins for dynamic objects, etc. All right, so it's curved around that exclusion zone here, and it's heading up towards that waypoint. I might, because again, I want to get some sleep sometime tonight. I'll just speed that up a little bit, and so that it gets through this last track to land just a little bit faster. It is turning around. It's on the final approach. It should take it about a minute in simulation time to get up there. Or it's estimating 2.5 minutes to land, so about a minute because we're speeding up by a factor of 2. And then it'll go into a landing pattern up here. So it does this landing approach pattern, and meanwhile the Kraken is actually coming in for its final landing here. There it is. All right, it's going to come in and land. So it's actually coming in at a similar time to each other, but the Kraken will be well and truly landed before the porter gets on the ground. So there's the porter coming up here, and it's going to go around these waypoints and again look for airspace clear, make sure things are not contended with other obstacles in the air. And I'll drop the speed up back to 1 so we can watch the landing in normal time. And it's decided to go straight here because airspace is clear. If there was any obstacles around, it would have started circling here in its landing pattern before finally going for the vertical landing up here. So it's now coming in for the landing approach. Just to give you an idea of the scale, these yellow lines here are a distance of 1 kilometre apart. So it's got a couple of 100 or so meters here on the landing approach that it needs to do. So it's coming up for the final landing. There it is, and it's aiming to land up here. There's the vertical landing position. Oh, the Kraken's actually wandering about on the ground. You have to have a look at that. I think it's being wind affected. And no, I'm not sure it is actually the wind. I need to have a look into that as to why it's wandering about on the ground like that. It's actually disarmed, I believe. No, it's not. Okay, I'll look into that later. I think it's actually in data link loss. That's actually a bug, I think, because that's in data link loss. It's basically lost lost data link, and it went into one of the fail-safe things. So it shouldn't do that after the landing approach. There's a bug. So we'll look into that. Lots of bugs to look into. So it's in the final landing here down to 3 meters, 2 meters, 1 meter, and it's going to disarm in a few seconds, and then we will have landed and completed the mission. So that's how we're approaching the Outback Challenge this year. Whether things go quite the same in the real vehicle as in the simulation, we don't know, but we will post results, and you can follow things on the UAV Challenge Live Facebook page. Thank you for watching.